Have you ever considered how some of humanity's most profound discoveries aren't born from grand, calculated missions, but rather emerge from the discarded fragments of our darkest hours? Consider the aftermath of World War II. Across the muddy, scarred landscapes of Europe, military radar installations, once vital for tracking enemy aircraft, now lay dormant, obsolete, or simply abandoned. Yet within these rusting relics of conflict lay the dormant seeds of a revolution in our understanding of the cosmos, a revolution that would uncover the brightest, most enigmatic beacons in the entire universe. It was in this unlikely setting, in the late 1940s, that a new breed of scientists, driven by an insatiable curiosity, began to repurpose these instruments. British and Australian astronomers, among them the pioneering Dr. John Bolton and his dedicated team, saw not just scrap metal, but gateways to an unseen realm. They painstakingly reassembled captured German Würzburg radar dishes, not to scan for bombers, but to listen to the whispers of the heavens. This was the dawn of radio astronomy, a science that would unveil a universe entirely invisible to the human eye, a cosmos humming with energies previously unimagined. As these repurposed dishes swept the sky, they began to pick up signals unlike anything observed before. Astronomers were accustomed to diffuse radio emissions from vast nebulae, sprawling clouds of gas and dust that glowed faintly across the radio spectrum. But these new sources were different. They were powerful, incredibly intense, yet astonishingly compact. They appeared as point-like signals, almost as if they were individual stars. Yet when optical telescopes were aimed at their radio coordinates, there was nothing to see. No bright, familiar stellar objects, no wisps of glowing gas, just empty blackness where a colossal radio signal emanated. This was the cosmic anomaly, the persistent, unexplained ghost in the radio data. The meticulous process of identifying these so-called quasi-stellar radio sources became a painstaking endeavor. Pinpointing their exact locations on the celestial sphere presented immense technical challenges. Early radio telescopes lacked the fine angular resolution of their optical counterparts, meaning a radio source might be localized to an area the size of a full moon in the sky. Within such a vast patch, finding a faint, invisible object with a traditional telescope was akin to searching for a single grain of sand on an entire beach, blindfolded. These signals stubbornly resisted clear identification for years, becoming one of astronomy's most frustrating dead ends. Among these mysterious signals, one stood out for its sheer power and perplexing nature, an object catalogued as 3C-273. It was one of the brightest radio sources in the sky, a beacon of pure energy, yet its true identity remained hidden, a cosmic enigma taunting astronomers across the globe. For years, every attempt to match its precise radio position with a visible object in the night sky ended in failure, leaving scientists scratching their heads and rechecking their instruments. The ghost simply refused to reveal its face. Then, in 1962, a truly clever and somewhat audacious technique offered a breakthrough. British-Australian astronomer Cyril Hazard, working at the newly commissioned Parkes Observatory in Australia, conceived of using a cosmic game of hide-and-seek. He realized that as the moon, our nearest celestial neighbor, moved across the sky, it would periodically pass in front of, or occult, distant celestial objects. By precisely timing when the radio signal from 3C273 winked out behind the lunar limb and then reappeared on the other side, Hazard could trace its exact trajectory and, in turn, pinpoint the source's true position with unprecedented accuracy. This technological ingenuity was not the result of a planned astronomical mission, but a creative exploitation of celestial mechanics. It was a testament to the human mind's ability to turn natural phenomena into scientific instruments. The lunar occultation data from Parkes provided coordinates so precise they were like a street address for 3C273. This level of accuracy, previously unattainable for radio sources, allowed optical astronomers to finally direct their powerful telescopes with pinpoint precision to the elusive object, setting the stage for a revelation that would forever alter our understanding of the universe. The clues, buried for so long in noisy radio data, were finally leading somewhere. The initial assumption that these were merely strange, radio-loud stars nestled within our own Milky Way galaxy, a theory held firmly by many, was about to be spectacularly shattered. A scientific revolution, born from the unlikely marriage of wartime technology and pure astronomical curiosity, was now poised on the precipice of discovery. This was the story of the puzzle before the solution, a compelling testament to the sheer human ingenuity required not just to answer, but even to frame the right question about these bizarre celestial objects. The ghostly radio signals of the previous chapter, stubbornly refusing to reveal their true nature, finally had a precise celestial address. It was a cosmic invitation sent across billions of light-years, and on the frigid night of February 5, 1963, one man was about to accept it. That man was Maarten Schmidt, a brilliant Dutch-American astronomer who now stood before the colossal 200-inch Hale telescope at Palomar Observatory in California. Armed with Cyril Hazard's meticulously calculated coordinates for the elusive radio source known as 3C273, Schmidt had pointed humanity's most powerful optical eye towards this cosmic enigma. His mission was to capture its spectrum, the ultimate cosmic barcode that would finally reveal its true identity. As Schmidt stared at the photographic plate, a wave of frustration began to wash over him. The plate, fresh from its chemical bath, displayed a series of strange, broad emission lines. These were the spectral fingerprints of the light emitted by 3C273, yet they matched no known element, no familiar chemical process. Astronomical spectroscopy is a powerful tool, acting like a cosmic prism that breaks light into its constituent wavelengths, revealing not only an object's chemical composition, but also its temperature, density, and crucially, its motion. For years, the world's best astronomers had grappled with these impossible patterns, each attempt to decipher them leading to a frustrating dead end. Hours turned into what felt like an eternity as Schmidt meticulously compared the alien spectrum against every known celestial signature. The lines of 3C273 simply did not conform. They were wide, blurred, and unlike anything seen before from a star or galaxy. His mind raced, seeking any pattern, any hint of recognition in the jumble of light. The prevailing theory still held that these radio ghosts were strange, compact stars within our own Milky Way galaxy, yet their spectra screamed otherwise. The mystery deepened with every passing moment, threatening to become another insoluble puzzle in the vast cosmic expanse. Then, With a sudden, almost jolt-like clarity, the impossible clicked into place. What if the lines were not from an exotic, unknown element, but were in fact the most common element in the universe, hydrogen? What if they were simply shifted, not subtly, but to an unbelievable degree towards the red end of the spectrum? This radical idea, a profound leap of intuition, instantly transformed the puzzling jumble into a coherent, albeit astonishing, pattern. This phenomenon, known as redshift, is a direct consequence of the universe's expansion, meaning that light from objects moving away from us gets stretched to longer, redder wavelengths. The calculation was swift and breathtaking, a redshift of 15.8%. Such an extreme shift was absolutely unprecedented for any object previously observed. According to Hubble's law, which links an object's redshift to its distance and the expansion of the universe, this implied a truly staggering distance. 3C 273 was not a star nestled within our own Milky Way, as many had assumed. It was an object nearly 2.5 billion light-years away. To put that immense span into perspective, the light that Schmidt was analyzing had begun its journey when complex multicellular life was only just beginning to appear on Earth, billions of years before the first dinosaurs roamed our planet. The profound implications of this single observation immediately resonated through the scientific community, shattering the prevailing view of a relatively static universe. For 3C 273 to be visible from such a staggering distance, it had to be unbelievably luminous, outshining entire galaxies by a factor of hundreds. Imagine our own Milky Way galaxy, a sprawling collection of hundreds of billions of stars, yet this seemingly point-like object was hundreds of times brighter. This immense energy output was completely inexplicable by any known physics, far beyond the capabilities of nuclear fusion, the process that powers stars. Schmidt's discovery, initially met with a healthy dose of disbelief and skepticism, rapidly transformed the enigmatic radio ghosts into the most luminous and distant objects ever observed. They were no longer a mere local curiosity within our galactic neighborhood, but had become a profound cosmological puzzle. This entirely new class of celestial body, so unlike anything seen before, demanded a new name. Born from the contraction of quasi-stellar radio sources, the term quasar was coined, a name that would echo through the annals of astrophysics. It marked the dawn of a new era, an era in which scientists were now faced with the monumental task of explaining the existence and incredible power of these cosmic monsters. We have identified the quasar, a cosmic anomaly that screams with the energy of hundreds of galaxies from billions of light-years away. But the true enigma, the profound paradox, lies not in its impossible brightness, but in its dark heart. How can the most luminous objects in the entire universe be powered by the very things that consume light, supermassive black holes? The answer is a spectacular testament to cosmic inefficiency, a glutton's feast where the mess created is far more brilliant than the meal itself. The prevailing image of a black hole is often that of a perfect, silent cosmic vacuum cleaner, effortlessly sucking everything into its inescapable maw. But the engine driving a quasar is anything but silent, and far from perfect. It is, in fact, an incredibly messy eater, and it is precisely this inefficiency that makes quasars shine with such ferocity. In the mid-1960s, brilliant minds like Yakov Zeldovich in the Soviet Union and Edwin Salpeter in the United States independently began to theorize the unthinkable, that the immense energy output of these newly discovered quasars could be generated by matter falling onto a massive dark object. They imagined gas and dust, not directly consumed, but instead locked in a frantic death spiral around a central gravitational behemoth. This is the core concept, accretion. As gas, dust, and even entire stars are drawn in by the black hole's immense gravity, they do not simply plunge straight down. Instead, they flatten into a vast, swirling disk, sometimes millions of kilometers across, called an accretion disk. Within this cosmic maelstrom, material spirals inwards, picking up incredible speed. But as it does, particles collide, generating immense friction, and powerful magnetic fields become twisted and tangled, creating a turbulent inferno. The heat generated by this gravitational gridlock is staggering, reaching temperatures of millions of degrees Celsius, far hotter than the surface of any star. And at these extreme temperatures, the material radiates away a huge fraction of its potential energy, not after it crosses the event horizon, but before it ever reaches the point of no return. Consider it a cosmic traffic jam of epic proportions. The energy released by cars grinding to a halt and crashing together in a mile-long pileup is far greater than the kinetic energy of the few vehicles that eventually make it to their destination. In a quasar, the light we see, the blinding beacon that penetrates billions of light-years, is the radiant scream of matter being violently decelerated, heated, and compressed, all before the black hole itself ever gets to eat it. The vast majority of the potential energy is converted into light, X-rays, and radio waves, escaping into space, long before the material vanishes from our universe forever. This incredible outpouring of energy is not limitless, however. Nature has a built-in thermostat, a delicate balance discovered decades earlier by the visionary British astrophysicist Sir Arthur Eddington, though he applied it originally to stars. This is the Eddington limit. It describes the point at which the outward pressure of the light and radiation emitted by the accretion disk becomes so powerful that it literally pushes back against the incoming fuel. The sheer force of the emitted photons, billions of times more powerful than the light from our sun, becomes strong enough to blow away the very gas and dust attempting to feed the black hole. This elegant mechanism of self-regulation explains how quasars can maintain their gargantuan luminosity for millions of years. If the black hole tries to feed too quickly, the outward pressure of its own light intensifies, pushing away its fuel, effectively preventing it from gorging itself into self-destruction. It is a dynamic equilibrium, a cosmic balancing act where the black hole's ravenous hunger is kept in check by the very light it generates. This ensures a steady, prolonged, though incredibly intense, output of energy. And what about those powerful, narrow jets of plasma that often shoot out from the poles of some quasars, extending for hundreds of thousands of light-years? These are another consequence of the chaos within the inner accretion disk. They are a cosmic pressure release valve, a byproduct of the violently tangled magnetic fields that whip around the black hole's poles. These magnetic fields act like cosmic slingshots, channeling and accelerating charged particles to nearly the speed of light, ejecting them in tightly collimated beams that slice through the intergalactic medium. The quasar, then, is not merely a dark, hungry maw, but a complex, balanced, and fiercely self-regulating system, born from the most extreme physics known to humanity, a beacon truly lit by the colossal waste heat of a black hole's imperfect, spectacular feast. We have peered into the enigmatic heart of the quasar, a blinding beacon fueled by the insatiable hunger of a supermassive black hole, a paradox of light born from darkness. But what if these colossal powerhouses are more than just distant, isolated curiosities? What if they are not merely passive lighthouses, but rather cosmic forces, actively shaping the very galaxies that host them, dictating the fate of billions of stars? The modern understanding of our universe reveals a profound truth. Quasars are the universe's master architects. This radical recontextualization centers on a concept known as active galactic nuclei feedback, a theory that has become fundamental to explaining why galaxies appear the way they do across the vast cosmic tapestry. Consider the immense radiation pressure and the relativistic jets, those powerful beams of plasma blasting outwards from a quasar's core. These aren't just isolated phenomena. They exert a profound galaxy-spanning influence. Think of it as a powerful cosmic wind, a force so immense it can literally sweep through the host galaxy, heating and expelling the cold gas reserves that are absolutely essential fuel for forming new stars. This process is known as negative feedback, and its effects are transformative. By driving out the star-forming gas, it effectively quenches star formation, prematurely aging the galaxy and often determining its ultimate shape and size. Without this crucial mechanism, our understanding of galactic evolution simply falls apart. Cutting-edge computer simulations, such as the Illustris TNG project, starkly demonstrate this. When scientists run these complex models of the evolving universe without including the effects of active galactic nuclei feedback, the results are drastically different from what we observe. These simulated universes produce galaxies that are far too massive, bloated giants relentlessly churning out young blue stars, a stark contrast to the diverse array of galaxies we actually see. The evidence for this cosmic landscaping is not confined to theoretical models. It is observed directly across the cosmos. X-ray observatories, like NASA's Chandra X-ray Observatory, and radio telescopes, such as the Very Large Array, have captured astonishing images. These reveal colossal bubbles and vast cavities, stretching for millions of light-years across, blown into the intergalactic gas by the powerful jets of long-dead quasars. These are the fossilized imprints of past activity, monumental scars left by engines that raged billions of years ago. It is tangible proof that even after their brilliant reign ends, the legacy of a quasar continues to resonate through the cosmic medium. Yet, the influence of quasars is not always destructive. In a fascinating twist, there is also evidence for what scientists call positive feedback. In some scenarios, the shock waves emanating from quasar outflows can actually compress existing gas clouds. This sudden compression can, paradoxically, trigger localized bursts of star formation, igniting new stellar nurseries before the ultimate, powerful clearing of the galaxy's fuel supply. It is a delicate balance, a cosmic dance where the same powerful forces can both create and destroy, leading to a complex interplay that sculpts galactic landscapes. Ultimately, This recontextualizes quasars from mere astronomical curiosities into the true master architects of their environments. They are the powerful weather systems that dictate the climate of an entire galaxy, determining how many stars are born, how quickly they age, and what their final form will be. It is the very reason why colossal galaxies like our own Milky Way are not still furiously churning out stars today. From the gargantuan galaxy sculpting power we have observed, one might logically deduce a gradual, majestic evolution. But what if the universe's most powerful engines, the blazing quasars that light up the cosmic dawn, began not with a slow, incremental buildup, but with an impossible, rapid birth? This is the profound paradox at the absolute frontier of modern cosmology, a mystery that challenges our deepest understanding of how the cosmos came to be. We peer into the farthest reaches of space, back to an era when the universe was barely a toddler, less than 1 billion years old. And what do we find? Not infant black holes, modestly growing from stellar remnants, but fully formed titans. Observations reveal quasars already boasting masses equivalent to a staggering 1 billion times that of our own Sun. Consider the sheer scale of that number. A solitary object, formed in the universe's infancy, weighing as much as 1,000 million suns. The critical timing problem becomes immediately apparent. How did these gravitational behemoths gorge themselves so massively, so quickly, in such a short span of cosmic time? It is a question that gnaws at the very foundations of our cosmological models. Scientists have grappled with this conundrum, proposing two leading, competing hypotheses, each offering a tantalizing glimpse into the universe's earliest, most extreme conditions. The first is known as the light seed model. This theory posits that the very first black holes, the primordial seeds from which today's galactic monsters grew, originated from the collapse of the universe's inaugural generation of stars. These were no ordinary stars. They were colossal, ephemeral giants known as population 3 stars, composed solely of the universe's pristine primordial hydrogen and helium. They were hundreds of times more massive than our Sun, burning fiercely and living short, explosive lives that ended in a direct gravitational collapse, leaving behind black holes of perhaps tens or hundreds of solar masses. From these relatively modest beginnings, the challenge then becomes explaining how they accreted matter and grew into billion solar mass titans in mere millions of years. Yet, a second, far more exotic and perhaps even more dramatic theory exists, the heavy seed, or direct collapse black hole, often referred to as DCBH model. This audacious hypothesis suggests that, under exceedingly rare and precise conditions in the early universe, gargantuan clouds of pristine gas, untouched by the heavy elements forged in later stellar generations, could have bypassed the star-forming phase entirely. Instead, these vast, cold reservoirs of hydrogen and helium, without the usual cooling mechanisms to break them into smaller fragments, collapsed directly under their own immense gravity, spiraling down into a singular, colossal object. The result: a black hole born not from a star, but from a direct gravitational implosion, possessing thousands of solar masses right from its inception. It is a cosmic shortcut, a direct route to building a supermassive entity from the earliest moments. The quest to discern which of these pathways the early universe truly followed demands an instrument capable of peering back through time, sifting through the faintest whispers of light from the cosmic dawn. This is where the James Webb Space Telescope, the magnificent eye in the infrared, assumes its uniquely crucial role. Unlike optical telescopes, the James Webb Space Telescope's infrared vision is specifically designed to detect the light from the most distant, red-shifted objects in the universe, light that has been stretched by the universe's expansion from visible wavelengths into the infrared spectrum. It is literally capable of seeing the earliest epochs, acting as a cosmic time machine. And the James Webb Space Telescope is already delivering astonishing results. Take, for instance, the recent discovery of an extremely distant quasar designated JAGE GS0. This remote beacon, observed when the universe was incredibly young, is providing critical data, testing the very limits of these competing formation models. The telescope's sophisticated instruments are not just detecting these ancient light sources, they are dissecting them, analyzing the chemical composition of their host galaxies. Why? Because the heavy seed or direct collapse black hole model predicts a distinct signature. These primordial black holes would have formed in an environment dominated by pristine, metal-poor gas, essentially the raw, untouched material of the early universe. Finding such a signature, a galaxy still in its unblemished infancy, would be a powerful piece of evidence in favor of the direct collapse black hole scenario. This is not a solved puzzle. It is an ongoing, vibrant scientific investigation, a live debate playing out across the pages of astrophysical journals. Astronomers, armed with the James Webb Space Telescope's unprecedented capabilities, are meticulously sifting through the faintest, oldest photons imaginable, searching for the telltale clues, the seeds, of today's galactic monsters. It is a profound detective story, connecting the physics of the very small, like the delicate processes of star formation, with the grandest, most mind-boggling scales of cosmic evolution, all unfolding before our very eyes. We have journeyed through the cosmic expanse, following a trail of light that began not in the heavens, but in the unlikely aftermath of a world at war. From a persistent radio signal, an anomaly born from repurposed military technology, we unveiled a universe-shaping engine. We discovered the quasar, a blinding beacon of energy powered by a profound gravitational paradox. The incredible brightness is a byproduct of the messiest eater in the cosmos, a supermassive black hole. But this journey isn't just about understanding distant phenomena, it is about understanding our own cosmic heritage, the profound connection between these ancient monsters and the very existence of our galactic home. The central truth of the quasar's existence is its dual nature. They are both destroyers and creators, simultaneously laying waste to nascent star fields and fostering the conditions for future life. To truly grasp this, we must transport ourselves back to a violent, brilliant period in the universe's adolescence, a time roughly 10 billion years ago. This era is now known to astronomers as the Quasar epoch. During this turbulent age, galaxies were not the serene, majestic spirals we see today, but were actively forming, colliding, and merging at a furious rate. And within their chaotic cores, their central supermassive black holes were feasting voraciously, growing at incredible speeds, their accretion disks blazing with unparalleled intensity. This chaotic phase was not merely a side effect of cosmic evolution, it was a necessary, even vital, step in shaping the universe we inhabit. The immense energy released by these ancient quasars, through both their powerful radiation and their colossal jets of plasma, exerted a profound influence across billions of light-years. This cosmic feedback sculpted galaxies like our own Milky Way, acting as a massive, universe-spanning force that regulated their growth. Think of it not as a gentle breeze, but as a hurricane of energy sweeping through galaxies. This stellar tempest pushed away vast reservoirs of cold gas, the very fuel needed for new stars to ignite, thereby limiting the runaway growth of galaxies and ensuring they didn't all become impossibly massive, blue behemoths. Furthermore, this extreme cosmic activity played a crucial role in enriching the intergalactic medium itself. The violent outflows from quasars, sometimes reaching speeds of millions of kilometers per hour, carried not only the raw materials of galaxies, but also heavier elements. These elements, like carbon, oxygen, and iron, were forged in the hearts of the massive, short-lived stars whose formation was both triggered and destroyed by the quasar's influence. Without this chaotic dispersal, the universe would be a much emptier, far less chemically diverse place, lacking the building blocks essential for planets, and ultimately for life itself. This revelation forces us to confront a profound, reflective question. Are we, in the present cosmic moment, living in the quiet twilight of the universe, after the great fireworks of the quasar epoch have finally died down? Our own Milky Way, for instance, is no longer forming stars at the furious rate of its youth. Its central supermassive black hole, Sagittarius, a star, is largely dormant today, a mere whisper compared to the raging inferno of a quasar. The answer appears to be yes. The most dramatic episodes of galactic growth and black hole feeding seem to be behind us, leaving a universe that is, by comparison, calmer and more settled. This realization frames quasars not as alien, distant objects, wholly separate from our existence, but as a fundamental, intimate part of our own cosmic lineage. The very same physics that powers these brilliant extreme beacons, these monstrous engines of destruction and creation, is directly responsible for the stable, life-friendly environment of the Milky Way today. It is the legacy of their ancient violent reign that has allowed for the slow, steady birth of solar systems like ours, where planets can orbit for billions of years, creating the conditions necessary for complex life to emerge. These objects, once mere puzzles to be deciphered, are now understood as the grand sculptors of our galactic home. From the deepest, most extreme darkness of a feeding black hole, radiating colossal amounts of waste heat, came the most brilliant and ultimately life-shaping light that illuminated the path to our existence.